Hello and welcome. The purpose of this video is to talk you through finding an empirical formula experimentally. Now, I'm not going to walk you through step by step each individual problem in homework 5. The idea is that you watch this video, and if you watch this video and understand what I'm doing, then you'll be able to then go back to the document where it walks you through step by step by step how to do each of these processes. So I'm just going to approach this as if I were starting this lab and I were about to do my data analysis. All right, so I've used the simulation from University of Oregon and collected my data here. And notice it's really important that you've reported your data to the precision that the instrument gives us. So the instrument went to 4 decimal places, so I'm showing 4 decimal places for each of my measurements. And we're going to go ahead and jump in here. Before I start, I need to remind myself what was the chemistry that was happening. So I started with an empty crucible, which is just a container, and I took its mass. I then had a crucible, I heated it, and then I took its mass. I then had my crucible, I added some CuX, OY, my copper oxide, and I took its mass. I then heated the red CuXOY, allowing oxygen to enter. And I, of course, heated it. That's a flame. And then when my product was formed, which I knew because I had a black product, when my product was formed, I took its mass. You'll recall the purpose of this step was to remove any impurities from the crucible. Really, I just really wanted to make sure that that crucible was totally clean. I want to evaporate off any impurities. And you see there actually were impurities in my crucible because my mass decreased. And then this part was the reaction. One thing to notice that the simulation didn't really show. In the lab, you would actually take this mass several times, and same with this really. And you would heat until a constant mass. So you would just keep heating, and checking the mass until you're sure the mass isn't changing. Okay. The reaction that happened was CuXOY, some unknown copper oxide, reacted with oxygen in the air to yield CuO. It's important to keep this in mind. If you go to Cognity to get help with this section, which is great, I always recommend Cognity. If you go to Cognity to get help with this section, they do have an experiment like this, but their experiment is different. They do not start with an oxide and end with an oxide. They actually start with just magnesium, so that obviously affects their calculations. It's important you're following along with each calculation that I do and understand that you need to set up the calculations that work for your experiment. So this is going to work for this reaction. It's possible to do a very similar experiment with a slightly different reaction. For example, not starting with an oxide. All right, so let's get into it. I'm going to start by finding the mass of each of my species here. So the mass of CuXOY, the mass of O2, and the mass of CuO. I'm actually going to start with the mass of CuO. I'm going to take the mass of the crucible lid and CuO and subtract out the crucible and lid to get just the copper oxide. So that's 5.9577 minus the clean empty crucible, which would be the 4.5. So I have 5.9, see if I can get these to show up at once, 5.9577. 0.9577 grams minus 4.5000 grams equals 5.9577. 1.4577 grams. Okay. Going to find the mass of my reactant. Very similarly, the mass of the crucible and lid plus the reactant minus the crucible and lid. 5.8053. This might feel a little weird to you just because how the simulation was set up and how you had to find the mass. You probably found this number by adding the crucible, and now I'm asking you to subtract it. The reason being, I set up this table exactly like it would be set up in a lab. I know the simulation gets a little funky there. Minus 1.3053. All right, so I now know that these are my reactants and this is my product. Based on the law of conservation of mass, the mass of my reactants must be equal to the mass of my product. So I know the mass of one product. To find the mass of the other, I'm just going to subtract the total mass of my reactants, which would be the same as the mass of the products. It's just law of conservation of mass, to get the mass of oxygen. Zero 0.1524 grams. Right, as long as I put everything into my calculator correctly, I now have the mass for each of my species in my reaction. This is a good place to stop, pause, make sure you're understanding before you move on. All right, my next step here, I'm going to focus in on this product here, CuO. And I'm going to use this product to find out how much copper did I have and how much oxygen did I have, knowing that the amount of copper in the reactant in the products needs to be the same as the copper in the reactants. The oxygen in the products needs to be the same as the oxygen in the reactants. I'm going to find out this how much bit instead of in grams in terms of moles, because I know moles are really helpful to me for empirical formulas, for anything that I'm looking at really. So I'm going to start with my grams of CuO. 4577 grams of CuO. And again, I'm trying to find the amount in moles for each individual part of that molecule, meaning I'm going to need to use subscripts as molar ratios. Well, if I'm using molar ratios, I better get the Cu into moles. In order to do that, I will need the molar mass. So the molar mass of CuO, let's check Cu, 63.55. Let me write this correctly. Notice I'm using the data booklet, not another source. Oxygen is 16. 63.55 plus 16. 79.55 grams per mole. Okay. So I'm going to convert the CuO, this grams of CuO, into moles of CuO. Times 1 mole of CuO. Again, now I'm looking for just oxygen. So 1 mole of CuO. There's 1 mole of oxygen in every mole of CuO. Yes, I know this step seems a little silly because it's multiplying by 1 over 1, but you wouldn't always have a ratio of 1 over 1. That's just because this equation happens to have the subscripts 1 and 1. So we still need to show our work, and we still need to remind ourselves that we're ending in moles of oxygen. So this gives me, I'm just going to put this into my calculator, 0.01832 moles of O. Great. Now I'm going to do that for copper as well. 7 grams CuO, 79.55 grams CuO, 1 mole CuO. Now that I'm in moles of CuO, I can convert to moles of just one thing in that molecule. And this math, I'm actually end up multiplying out exactly the same numbers. So 0.1832 moles of Cu. Notice if you're following along here, your numbers will not be the same as mine. My numbers are dependent on the data that I collected. You'll have added a slightly different amount of CuXOY. I think your crucible was the same mass, but you'll have slightly different amounts in these last two, and so your numbers will be different, even though your process should be the same. That is the idea. Okay, so let's go back to the reaction that happened. Let's remind ourselves. And I just discovered that I had 0.01832 moles of Cu in the product that I formed, and 0.01832 moles of oxygen in the product that I formed. Another good place to pause, make sure you're understanding. All right, let's take a look at Cu. I see I have Cu in my reactants, Cu in my products. Well, the only place I have Cu in my reactants is right here. The only place I have it in my products is right here, meaning that the amount that I have in my products is exactly the same as the amount I have in my reactants. Great. What about oxygen? Well, oxygen actually occurs in two reactants. There's some oxygen in CuXOY and some in O2. So both of these oxygens together need to give me 0.01832 moles of oxygen. Notice not moles of O2, but moles of just oxygen. Well, there's a little bit more information I have. I don't know how much oxygen I have in CuXOY. I do know how much O2 reacted, at least in grams. I have that amount right here, the mass of O2, 0.1524. Just going to make sure I wrote that down correctly. It looks like I did. Yes, okay, 0.1524. 0.1524 grams of oxygen. Well, that's helpful, but right now I have grams of oxygen. Let's choose the right color. Okay. I have grams of oxygen and a total moles of oxygen. Well, I can't really compare grams to moles, so it looks like I should convert this amount to moles so that I can do some comparisons. So let's take that amount of oxygen, of O2, 0.1524 grams of O2. All right. Now, this molecule, O2, let's find the molar mass. We know each oxygen has a molar mass of 16 times 2 because there's 2 oxygens per molecule. Gives me 32 grams per mole. So 32.00 grams of O2 for every 1 mole of O2. Well, now I'm close, but remember I had moles of O here, and I'm in moles of O2, so kind of tricky, but I do need to get into moles of just O. O2, 1 mole of O. All right, 0.1524 divided by, gives me 0.0047625. I'm going to write all the sig figs that I have, moles of O. In the O2 gas that entered into the reaction. All right, so if I now know that this is 0.0047625 moles of O, this total had to be 0.01832 moles of O. Well, now I can take the total, subtract the amount of O that was in O2, and get the amount that was in, the amount of oxygen that was in CuXOY. So the amount of oxygen in CuXOY, I'm going to take the total moles of O in my reactant and subtract the moles of O in the O2. In, I can say here, both reactants. Okay, so 0.01832. 0.01832 moles of O in both reactants minus 0.0047625 moles of O. And notice I'm now in the same unit, so I'm allowed to subtract these. Cool, sorry about that. 2. And I'm not rounding any of my answers until the very end. That's an important thing in chemistry, that you don't round early. You keep as many decimal places as you can until you get to the very last step. Moles of O in CuXOY. All right, so up until now, this is chemistry we have done before. We're just converting between grams and moles, and then also using subscripts as molar ratios. Our final step is to actually do the empirical formula. So the worksheet does walk you through exactly how to do this. Let's take a look at it here together though. This is another good place to pause. Make sure you've understood everything so far before you move on. So I'm going to fill in the amount in moles that I have for Cu and O. So for Cu, I have 0.01832 moles. 0.01832. We got that number way at the beginning. For oxygen, I just found there's 0.0135575. All right. Now, I take a look at these two numbers. I decide which one is smaller. Indeed, 0.0135575 is smaller. 0.0135575 is smaller. And I divide both numbers by the one that's smaller. 0.0132. All right, here is where it gets a little bit weird, but what you need to do here is you need to actually round your answers. And so let me put this in my calculator. And this is why it's helpful to have all of the significant figures. Okay, so the number I'm getting in CuO is 1.35. So 1.35 technically rounds to 1, right? And of course, these divided by each other. or 1. This is looking a little strange to me, just because we wouldn't have really started. Doesn't really make sense to start with CuO and end up with O. In empirical formulas, if you round at the step, or excuse me, if you do the division in the step, that got a little strange. Let's have this go away. If you do the division in this step and your answer is close to a 0.5, you can report that. So let's say I decide that this 1.3 that I got for Cu is actually, it's pretty close given experimental uncertainty to 1.5. Well, if your answer is close to 0.5, then you would multiply both coefficients by 2. So I would say that for my data, either formula would be reasonable to report, either CuO, or maybe I decide that that 1.35, it rounds up to 1.4, which is almost 1.5. Empirical formulas are a little bit of a judgment call, is more like Cu 1.5, and then I'm just going to multiply both subscripts by 2. So 1.5 times 2 is 3. O times 2, or excuse me, 1 times 2 is 2. I think some people got answers that were maybe a little odd in their empirical formula data. I think that's more of a result of the simulation and the fact that you're collecting real data that has uncertainty. The important thing is that you understand how to do the calculations. I know this last step is a little strange. It is a little bit of a judgment call to decide if you need to multiply both answers to 1.5 on an assessment. I would make that really, really, really clear. But the key is you're finding the ratio that exists for both subscripts. So you're taking the amount of moles and then you're dividing by the smaller amount. If the answers round to a close whole number, then you just round and leave it. If the answer rounds to 0.5, then you multiply both coefficients by 2. So I think I could make an argument with my data based on uncertainties that either answers are okay here. I don't want you to focus so much on if your actual empirical formula makes sense. The important thing is you're understanding the steps. So I hope that helped. Let me know what questions you have. I know this takes a couple repetitions. This is a little tricky to get the first time, but you're all very capable of doing this. All right, thanks for watching.